In this video, we're going to see how to use the quotient rule to divide radicals. So the quotient rule is one technique that could be used. Our first step is to simplify the numerical portion of the radicals. Our second step will be to simplify the variable terms under the radical if there are any. In example 1, we have the square root of 75 divided by the square root of 3. So when we look at these radicands, 75 and 3, we notice they are not perfect squares, and 3 is already a prime number. So the technique that was going to help us here is to simply use the quotient rule. The quotient rule will allow us to take these radicals and write them under one radical term instead of separately. So we would have a fraction under our radical as 75 thirds. Well, 75 is divisible by 3, and that makes exactly 25. So the square root of 25 is what we really have under the radical. Now we hopefully recognize that 25 is a perfect square, so our final answer is going to be 5. So don't worry if you have a denominator with a radical that is not a perfect square. Use the quotient rule to simplify 75 thirds to make 25, and now we do have a perfect square. In example 2, we have the square root of 48 divided by the square root of 2. Again, our denominator is not a perfect square, and we really don't like leaving square roots in the denominator. So I'm going to put these two terms together under one radical, and this is using the quotient rule. So the fraction 48 halves now is under one radical. 48 divided by 2 would give us 24. So we have been able to eliminate the fraction under the radical, and we have 24. Since 24 is not a perfect square, I'm going to use our factor ladder and divide 24 by prime factors. I could start with 2 since it's an even number, and that would give us 12. Divide again by 2 to get 6, divide by 2 to get 3, and then divide by 3 to get 1. Since we are dealing with square root, I'm looking for perfect squares or pairs of factors. So a pair of 2 would make 4, and then 2 and 3 are different factors, so that gives us 6. Now these are the factors that would remain under the radical. So the square root of 24 is the same as square root of 4 multiplied by square root of 6. Since 4 is a perfect square, we'll be able to simplify and clear 2. But remember where 6 comes from. 2 times 3, since there are no perfect square factors, 6 will remain under the radical. So this final answer is 2 square roots of 6. In our last example, we have numerical bases and variable bases. So the first thing I'm going to do is break apart the variables from the numerical portion. That would give me 245 divided by 5 for one radical, and then the other radical will have all of our variables. A cubed, b to the 7th c, is divided by a to the minus 2, b to the 4th, c to the minus 1. So starting with the numerical portion, 245 is divisible by 5 evenly, and that gives us the square root of 49, and that would be 7. That completely clears the radical. Now we'll go back and work with our variable bases. So what we want to look for here is how to collect each of these bases in one place with a positive exponent. So with our bases of a, we've got exponent 3, exponent minus 2. Remember, the base with the smaller exponent is the one that will shift across the division bar. So a to the minus 2 will be shifting up. So that's going to leave us a cubed multiplied by a to the positive 2. Remember, when that base and exponent shift, the exponent sign changes. Now b to the 7th compared with b to the 4th. 7 and 4 are what we're comparing. 4 is the smaller exponent, so that is the base that will shift. So when 4 shifts, it will become negative 4. So we had b to the 7, it's now joined by b to the minus 4. Comparing bases of c. Well, the base in the numerator doesn't even have anything written, so remember it's really positive 1. Now we can easily compare 1 with negative 1. So c to the negative 1 has the smaller exponent. So that will be the term to shift. So we had c to the 1 already in the numerator, and now c to the positive 1 will be joining it. So let's simplify what we have under our radical. This is product rule now. A cubed times a squared means we're adding exponents to get a to the 5th. For bases of b, we'll have 7 added to negative 4. That would be b cubed. And for c, 1 plus 1, so we have c squared. Now the only thing remaining is checking to see if any of these variable bases will clear the radical. So what we're doing here is dividing each exponent by the index. Since it's square root, we know the index is 2. So 5 divided by 2 is 2 remainder 1. 3 divided by 2 is 1 remainder 1. And 2 divided by 2 is 1 remainder 0. We'll go back to the numerical base of 7. With base A, 2 remainder 1 means 2 bases of A clear, but 1 remains under the radical. For base of B, 1 remainder 1, that means 1 base of B clears and 1 base of B remains. Base of C, 1 remainder 0, means base of C clears and none of base C remains. So let's put everything in order now. All the terms that have cleared the radical is what we start with. That's 7a squared bc. And then we'll write down the terms that did not clear the radical. In alphabetical order, that would be square root of ab. So our final answer is 7a squared bc multiplied by the square root of ab.